Temperature is the degree of hotness or coldness of a body. The degree of hotness or coldness of a body is known as temperature. And temperature is measured in Kelvin. That's the standard. It can also be measured in degree Fahrenheit. It can also be measured in degree Celsius. But this is the standard, Kelvin. All right. It is measured with an instrument called thermometer. All right. Used to measure temperature. The thermometer functions mostly with the aid of a fluid called thermometric fluid. But we have various types of thermometers. Okay. And I'm going to just walk you through them. All right. Before we talk about thermometric fluid property, let's first of all look at the types of thermometer. All right. Or, okay, let's just look at thermometric property in general. Okay. Thermometric property of a substance is the ability of a substance to respond to change in temperature. Depending on the way the substance responds, the ability to quickly respond to change in temperature. That's what the thermometric property of a substance. So usually we calibrate thermometers. Okay. We give it the one they call freezing point and boiling point. Okay. We put freezing point as the lowest mark. Then we put boiling point or steam point as the highest. All right. So that's how we usually calibrate the thermometer. But sometimes the scale can be divided. Okay. You divide these two scales. You can divide boiling by freezing to get your completely calibrated thermometer. But since you are not the one that is calibrating your thermometer, let's leave this one because thermometer, most of the time, they always come calibrated. Now, let's look at the types of thermometer real quick. Let's do that real quick because we have no much time. The types of thermometer. All right, types of thermometer. We have we have liquid in gas, liquid in glass thermometer, liquid in glass thermometer. This one, under this one, we have mercury, depending on the liquid choosing. We have alcohol, and so on and so forth. So these are the two most common liquids used in liquid in glass thermometer. So when we look at thermometric property here of a substance, so we are talking about the ability of this mercury to expand with change in temperature. It either expands or it contracts. When the temperature is low, mercury will contract. When the temperature is high, it expands. Okay, and it usually does that through in a narrow tube. All right. Okay, so mercury is usually better than alcohol when talking about thermometric property. All right, mercury is usually better. It expands better. It responds better to higher temperature than alcohol. All right, and alcohol evaporates. Alcohol has a lot of disadvantages because alcohol is invisible most of the time. When you are looking at it, it's invisible. But mercury will just be black. Okay, so number two types of thermometer, we have thermocouple. Okay, two metallic objects, metal A plus metal B added together to bring about a change in that detects a change in temperature. One of the couple expansion of metal. One of the couple expands when there is a lower temperature. Then the other one does expands when there is the temperature is higher. All right. So that's that for that. Then the third type of thermometer is gas thermometer. Gas thermometer is usually big. All right. And this thermocouple, we use metals like platinum. All right. Platinum for thermocouples. Those are the type of metal we use. Platinum / copper or silver and so on and so forth. All right. Then for gas thermometer is usually big. The thermometric substance is gas. Okay, gas, gas expands with increase in temperature. All right, so gas expands. When you increase temperature, the molecule of gas expand. So number 4, we have maximum and minimum thermometer. This thermometer is used to detect boiling points and ice points. Okay, it has 2 fixed points. Okay, one for steam points and the other one for freezing points. Don't forget that. And this thermometer usually requires a lot of calibration. This maximum and minimum thermometer. Then number 5, we have which other one have we not listed? We have pyrolimeter. Pyrometer, sorry. It's called pyrometer. All right. This one measures temperature through radiation. If you can remember, during the time of corona, you don't have to place it in contact with the body. Just bring it closer to the body that you want to measure the temperature, and you are going to detect the temperature. That's what pyrometer. And this pyrometer is also used industrially. Okay, those industrial machinery that is usually very hot, so they will not have to put it. They use it in furnace. All right, also using what? Furnace. All right, in burning furnace, they use it. Pyrometer. Hope we are not leaving out any other thermometer. All right, liquid in gas, thermocouple, gas thermometer, maximum and minimum thermometer. We have pyrometer. Okay, I think that's all. That's all the types of thermometer. So having explained this, should we look at temperature scale next? I think that's what we are going to look at now. Temperature scale conversion. All right, conversion of temperature. So we already discussed that in chemistry, but let's just do it. All right. So Celsius is usually from 0 Celsius. It's usually from 0 to 100. They pass 100. Okay, that's the scale for Celsius. Then for Kelvin, okay, Kelvin is also called what? Absolute temperature. All right, and just add the value, add degree Celsius. The formula is Kelvin is equal to degree Celsius plus 273. So if you want to convert degree Celsius to Kelvin, just add to 273, you get your Kelvin. Okay, so if you want to convert Kelvin back to degree Celsius, how do you do that? You minus 273 from the Kelvin to get back your degree Celsius. Something like this, equal to Kelvin minus 273. Abi, no be so. You get your degree Celsius back. All right. So at 0 degrees Celsius, so at this 0 degrees Celsius, this is equivalent to minus 273 Kelvin. 0 degrees Celsius is equal to minus 273 Kelvin. All right. Understand that. All right. Understand that. So let's look at conversion. Conversion from degree Fahrenheit to degree Celsius, or from degree Celsius to degree Fahrenheit. All right. So first of all, we are looking at conversion from degree Celsius, from degree Fahrenheit to degree Celsius. All right. So degree Fahrenheit to degree Celsius conversion. All right. So degree Fahrenheit is equal to 5/9. Okay. Bracket open. The degree. Okay, this one is conversion. Let's do degree Celsius first of all. Degree Celsius. Okay, we are converting degree Celsius to degree Fahrenheit. Sorry, we are converting degree Fahrenheit to degree Celsius. All right. So degree Celsius is equal to 5/9 bracket open degree Fahrenheit minus 32 bracket close. So this is the formula. So let's say you want to convert 1 degree Fahrenheit to degree Celsius. How are you going to do it? You are going to say, let's just continue for here. 5/9. You substitute your degree Fahrenheit. Bracket open. What is the degree Fahrenheit? 1 minus 32. You see? So we are now going to have 5 minus 5 times minus 31. Abi? Bracket close. Over 9. This times this. You get what you get divided by 9. You get your answer, your degree Celsius. Okay? Say you want to convert from degree Celsius back to degree Fahrenheit. So we are going to have degree Fahrenheit is equal to 5 over 9. Then we are going to have degree Celsius, bracket open, 32. All right? We now have to put this one in bracket. So you substitute and you get your answer. So here, since we are converting to degree Fahrenheit, I think most of the time we always use plus, but here don't forget to apply board mass here. Apply board mass. Since we are to plus, let's just make this easier so that we can apply board mass. Remember, we plus because we are converting to Fahrenheit, and you know that Fahrenheit is usually bigger. So what we'll do here is to just put this one in brackets, degree Celsius, then we put plus here, plus 32. So anything we solve from here, we are going to add it to 32 to get our answer. Okay, so let's say we have 1 as the degree Celsius. It's going to be 5 times 1 over 9. Okay, 5 times 1, which is 5, divided by 9 plus 32. Okay, it's going to be 9, 5 over 9, 5 divided by 9 plus 32. What you get here, you add it to 32 to get your answer. As simple as A, B, C, D. So that's how to convert. All right. So when next we come, we are going to continue with heat capacity. Or do we still have time? Let's just do heat capacity. All right. We do heat capacity and linear thermal expansivity. We do all of that. Let's do heat capacity. All right. First of all, we have to understand what is meant by quantity of heat before we look at heat capacity. What is known as quantity of heat? We have to understand that first of all. Quantity of heat. Quantity of heat is the heat transferred. All right. From one place to another. From one body to another. That's quantity of heat. That heat transferred. That's the quantity of heat now. From one place to another, from one body to another. All right. This gets us to heat capacity. Heat capacity. Given as capital letter C. Heat capacity is the what? The amount of heat energy required to raise the temperature of a substance by 1 Kelvin. Don't forget that 1 Kelvin, okay? By what? 1 Kelvin. The amount of heat required to raise the temperature of a substance, by 1 Kelvin. So, heat capacity is giving us heat capacity equal to quantity of heat over change in what? Change in temperature, right? Hereby Q is equal to quantity, T is equal to change in temperature, C here equal to heat capacity. That is the formula Shikina. And change in temperature is temperature 1, okay, temperature 2, minus temperature 1. That's the change in temperature. Or it can be given as theta 2 minus theta 1. They are all temperature. So this is how you get the change in temperature. All right. So next, let's look at specific heat capacity. Very easy. So specific heat capacity is the amount of heat. This one is not specific. Okay. Specific heat capacity is the amount of heat required to raise 1 kilogram mass of a substance. So here we have 1 kilogram. Okay. By 1 Kelvin. So this one now, the SI unit of this one will just be Joule. Since we are talking about heat, we say Joule per Kelvin. Kelvin raised to power minus 1. This one is the SI unit of heat capacity. So for specific heat capacity from the definition, 1 kilogram mass of a substance, we are going to have Joule per kilogram, okay, raised to power minus 1 per what? Kelvin raised to power minus 1. This is what the SI unit of specific heat capacity. All right. So the formula is given by Q. Specific heat capacity is Q. Heat capacity is capital letter C. Q is equal to what? MC theta. Then change in temperature. MC theta, change in temperature. Okay, this theta is the change in temperature. All right, but you can leave it like this: MC change in temperature or MC theta, anyone you wish. But let me just remove one. Okay, MC change in temperature, and I told you what change in temperature is. Either theta 2 minus theta 1 or temperature 2 minus temperature 1. So that's change in temperature for you. Now we move on to the rest. Looking at the rest, the latent heat. Okay, let's look at what this is giving. Okay, so this M is mass. Okay, M is equal to what? Mass. All right, C is equal to what? Equal to heat capacity. All right, as easy as that. We already talked about this one. Okay, so that's that for that. Remember to always do subject of the formula. All right, learn how to make subject of the formula. If you are given this one, Q now, which is the quantity of heat, for example, and you are asked, you are given C and you are asked to find Q. It's the same thing now. That's what they did here, just that they introduced mass there. So, but College of Nursing Sciences will not set more than all those basic questions, straightforward calculation questions. That's what they normally set. They are straightforward. It's not like JAM. So no fear. Just know the formula, understand the concept of what I'm teaching you. Okay. So how do we determine heat capacity and specific heat capacity? How do we do that? Remember, specific heat capacity is equal to the quantity of heat. All right. But the symbol is small letter c. But for heat capacity is capital letter C. Don't forget that. All right. So how do we determine specific heat capacity and heat capacity? How do we determine two of them? It's a flask now. Mix hot and cold substance and apply the principle of conservation of energy. So when you mix a hot substance and a hot water plus cold water, what are you going to get? You apply the principle of conservation of energy. Energy can never be created or destroyed but transferred from one form to another. So there's going to be heat transfer. Heat will move from one side. From the hot, energy is going to move from the hot to the cold until balance is stricken. All right. Remember the definition of heat capacity. It's not even heat capacity. The definition of heat transfer. All right. Okay. Or is it heat transfer or heat change? Quantity of heat. All right. Heat transferred. Okay. During a physical process, because now we are dealing with physics. All right. So we can use the mixture method to determine heat capacity and specific heat capacity. One, mixture method, the one I just explained. Cold water and hot water, or cold substance, cold liquid and hot liquid. So we can use this is what they call the use of calorimeter. All right, calorimeter. This is a device used to measure heat capacity, specific heat capacity and heat capacity. We use calorimeter to measure it. It's a flask. Okay, where you have this hot and cold substance in it. All right. We also have the electrical method to determine heat capacity and specific heat capacity. Electrical method. All right. What do? We use electrical heater. All right. Using electrical heater. We now apply this formula of Q equal to I square ROT. All right. So this is the formula you are going to apply using electrical method, where I equal to current, R equal to resistance, then T equal to time. All right. Okay. There is the Newton law of heat transfer. All right. The Newton law of heat transfer. Temperature loss or heat loss is equal to temperature gain. Okay. Temperature loss, temp loss, equal to what? Temp gain. This is the what? Like the general law we use in this heat capacity. Anything involving heat capacity, latent heat, okay, heat loss, heat gain. For example, we can say heat loss by hot water, because it's the hot water that loses the heat, right? Is equal to heat gain by cold water. All right. That's that for that. Now let's look at change of state. When this heat capacity brings about a change of state in a substance. All right. Let's look at that. Change of state. This is where we are going to look at latent heat of fusion, latent heat of vaporization. All right. First of all, let's understand what is latent heat. Latent heat is the heat absorbed or evolved during a change of state without temperature change. So the heat absorbed, latent heat. The temperature is latent, all right? The heat absorbed or evolve during a change of state without the loss of temperature, okay? Or without the change of temperature. No change of temperature, all right? No change in temperature, all right? Then inside this latent heat, now we now have the symbol of latent heat is capital letter L. We now have latent heat of fusion or specific latent heat, specific latent heat of fusion. This is what? From solid to liquid. That's melting, at melting point. So the heat required to convert 1 kilogram of a substance from solid to liquid, all right? At what? At melting point. That's what is called specific latent heat. And it is symbolized as small letter, then big letter, right? No, big letter L, then small letter F. Big letter L, small letter F. All right? This is the symbol. All right? Specific latent heat. All right? The amount of heat required to change the state of a substance, 1 kilogram of a substance. Don't forget about this 1 kilogram of a substance from solid to liquid at what? Melting point. Then we will look at the specific latent heat of vaporization. Latent heat of vaporization. Which is given as what is the symbol? That's LV. This is the amount of heat required to change the state of 1 kilogram of a substance, okay, from liquid to gas. Okay, at what? At boiling point. Some book will tell you at constant temperature. It's still the same thing, all right? At boiling point. So that's that for latent heat of vaporization, all right? You can see how we are taking it step by step. So this latent heat of vaporization, all this thing, there's nothing there. Just apply your normal latent heat. What is the formula of latent heat? That's what you are going to put there, okay? Specific latent heat. It said the heat absorb or evolve during the change of state of the substance without the change in what? Change in temperature. Okay, so if you are looking for quantity of heat, for example, quantity of heat will now be equal to MC theta, change in what? Temperature. This theta is change in temperature, or MC change in temperature. This is what you are using. All right, or you apply the other basic formula, which is C equal to, depending on what you are looking for, C, which is equal to Q over change in what? Temperature. All right, that's that for that. So do we understand the difference between evaporation and boiling? Evaporation and boiling, because that's also change of states. All right, evaporation is usually slow, boiling is usually faster. Then the second difference is that evaporation involves the what? Some part of the liquid, but boiling involves all parts of the liquid. So that's the major difference between evaporation and boiling. It's a very common question. All right, so get used to that. Difference between evaporation and boiling. Okay, and boiling happens at boiling point, but evaporation can occur at any temperature. So I've given 3 differences. The first is that evaporation is fast, evaporation is slow, boiling is fast. The second is evaporation involves part of the liquid, boiling involves the entire liquid. The third is that evaporation occurs at any temperature, but for boiling occurs at boiling point. All right. What are the factors that can elevate boiling points? Remember we treated hardness of water. So when we have impurity present, impurity which is like presence of other substances in the substance itself, that can raise boiling points. All right, it can raise boiling points. All right. It can also do what? Lower freezing points. Impurity too can lower freezing points. Therefore, impurity makes boiling point less sharp. Okay, it makes boiling point less sharp. It's no longer sharp. Okay, remember one of the methods to figure out the the purity of a substance through sharp melting and boiling point. All right. Can we quickly look at thermal expansivity, linear expansivity, and volume expansivity? We are going to do that, and with that we are going to draw the curtain. With that we are going to do what? We are going to draw the curtain. And in our next class we look at are we to look at gas law, or what we are going to do is that we are going to abandon that gas law because we are going to treat it in chemistry. So we can't treat it in chemistry and still treat it in physics because it's the same thing. Gas law is the same thing. Okay, Boyle's law, Sharp's law, they all remain the same. All the gas law, ID gas law, they are all the same. So we look at thermal expansivity. All right. First of all, we have to understand the meaning of expansion. Expansion of a substance, expansion of molecule. All right. So what is expansion or expansivity? Expansion is the increase in size of a substance or molecule. That's expansion. Increase in size of a substance or molecule. So the name we give to expansion depends on where the expansion is occurring. Is it occurring in a liquid? Is it occurring in a solid? Is it occurring in a gas? And what causes the expansion? Is it caused by heat? Okay. But most of the time, it is heat that brings about expansion. Okay, most of the time. So that's why it's usually called thermal expansion or thermal expansion. Anywhere you see thermal, just know it involves heat. Anywhere you see thermal, just know it involves temperature. All right. Don't forget that. So the first is thermal expansion in solid. That's expansion caused by heat is what? Thermal expansion. So thermal expansion in solid, we are going to look at about 3 of them. Okay. We also have expansion in liquid, but what we are looking at here is thermal expansion in solid. So the first one we are looking at is linear expansion or linear expansivity. Linear expansivity. What is linear expansivity? When metal expands in a straight line because of applied heat. Okay, it's usually given or represented with alpha. All right, it's usually represented with alpha. This is the sign of linear expansivity. Expansion in a straight line induced by what? Increase in temperature. And the formula is giving us length, change in length, which is what? The expansivity. This linear expansivity is equal to alpha length change in temperature. Just know that it's temperature that is causing it. Change in temperature will be included in the what? In the formula. So change in length equal to linear expansivity times length times change in temperature. All right. So we look at the next area expansivity. Number 2 is area expansivity. This is usually represented as beta. All right, beta. Present it as beta. And this is what? Fractional increase per unit area. What is the formula? The unit of area? Meter square. All right. So the thermal increase per unit area. All right. Per what? Unit area per degree rise in temperature. All right. So there is increase in area per degree rise in temperature. Increase in area of the solid. Okay. So the formula is giving us change in A, which is change in area. The effect of the area expansivity is equal to beta, okay, area change in temperature. You can see this one, alpha times length change in temperature, because it's linear length. All right, change in length, change in length, change in area, change in area. As easy as ABCD, no hard. Then the third one, which is what? Volume expansivity. Volume expansivity, which is beta. which is what? Gamma, sorry. Gamma. All right. And this one is what? Volume expansion per what? Per degree rise in temperature. So what is the volume expansion? Is going to be V. Okay, change in V, that's the change in volume, is equal to gamma, which is what? Volume expansivity. Gamma times volume, change in temperature. All right, that's the formula. All right, so let's now understand the relationship between the three. All right, so beta, which is area expansivity, this one is shortcut formula. Maybe they gave you linear expansivity to solve with, and they didn't give you all these things. They now ask you to look for the area expansivity. Beta is equal to, which is area expansivity, is equal to 2 times alpha. All right, 2 times alpha. It's not 2 alpha, 2 times alpha. Then we have gamma, which is what? Volume expansivity, which is equal to 3 beta, right? Is it 3 beta or 3 alpha? 3 alpha. So volume expansivity equal to 3 alpha. Linear area expansivity equal to 2 alpha. So this one is shortcut formula. Okay, because sometimes they might not give you all this volume, length. They will just give you only linear expansivity and tell you to look for the volume expansivity or the area expansivity. How then do you solve if you don't know all these shortcuts? Let's look at the application of expansion of solids. All right, which is linear expansivity, area expansivity, volume expansivity. What are the application? It's applied in railway. You know, the railway has to expand. Okay, has to expand so that iron doesn't get broken. Okay. So when train is moving, it has to expand. In bridges too, bridges expand too. In building strips, okay, buildings expand too. Bimetallic strip in thermostats, okay, bimetallic strip in iron, pressing iron, they expand with temperature, okay, so that temperature can be duly controlled. All right, that's that for the application. Okay, we have gas law here, and let's see if we are going to draw the curtain here at this point. Okay, before we go, let's just quickly treat gas law. Okay, or should we leave gas law so that we can treat it in chemistry? I think that's what we are going to do, because chemistry has more gas law, so that we just do everything together, and that will be it. So we do the gas law in chemistry. All right, let's just do the gas law in chemistry. Okay, so let's understand the formation of dew, mist, fog, and cloud. All right, so dew is as a result of condensation on the surfaces when air cool below dew points. All right, when air cool below dew points, that's where you get dew on the surfaces. Okay, on the surfaces, you can see it on the road, not really on the road, on surfaces. You can see dew here, you can see it on grasses in the morning. So it usually occurs when air cools below its dew point. All right, below its dew point, don't forget that. All right, the mist, it can also be called fog. All right, fog or mist is tiny water droplets suspended in air near ground. Okay, it's not a must that is going to be near the ground though, because you can still see mist if you carry glass now, or I do like this here on this board, you must see mist here, tiny water vapor. See, I can even feel it in my hand, tiny water vapor on this place. All right, that's mist or fog. All right, so we have cloud, which is water droplets that looks bigger when you look at the water droplets close, when it's close to the sky. Okay, it looks smaller. Sorry, it looks like cloud. Okay, it looks like smoke when you are seeing it from here, or when you go there, those are tiny water droplets. Okay, not really tiny, big water droplets. All right, they are just suspended on the atmosphere as cloud. When you go close, if you've boarded a plane before, you've boarded a flight before, if you flew before, you are going to understand what I'm talking about. When you see cloud, you notice that they are water droplets, large water droplets. All right, they can also be ice crystals. Okay, they are just suspended there. Sometimes, after some time, they are converted to rain, and it begins to rain. So rain is condensed droplets. Okay, condensed droplet that grow large enough to fall. So that cloud, it gets to a point, it grows large enough and it falls. Just like I told you, that is how rain is formed. All right. So what is dew point? Dew point is the temperature at which air is cooled, and you now have saturated vapor on the air. So when air becomes so cool, that point when air, dew point. All right, that point when air cools down and it begins to vaporize. That point is known as dew point. It begins to form dew, the point at which dew is formed. So we have humidity, which is the amount of water vapor trapped in air. When you are looking at the air, like you see, amount of water vapor trapped in air, that's known as humidity. Then what is relative humidity? The ratio of the actual pressure to the saturated vapor pressure times 100/1. So the actual pressure, relative humidity, actual pressure over saturated pressure times 100. So this is relative humidity, and humidity is measured with an instrument called hygrometer. Hygrometer. Relative humidity is measured with this instrument called hygrometer. Relative humidity is used to measure relative humidity. So we have different types of hygrometer. Okay, but one of the most common type of hygrometer is the dry bulb and wet bulb hygrometer, or the wet and dry bulb hygrometer. Wet and dry bulb hygrometer. All right, the wet and dry bulb type. There's a way you protect this bulb, the wet bulb and the dry bulb, so that you get accurate reading. All right. So the function of the dry bulb measures, it's dry, air temperature. Measures air temperature. Then the wet bulb, what's the function? Measures what? The vapor. Okay. It's usually covered with wet clothes. It measures it's used to measure vapor. Okay, this part measures the vapor. It's usually covered with wet clothes. Okay, so that it doesn't evaporate. Okay, it's used to measure vapor. All right. So what are the differences? What are the difference between humidity and relative humidity? Or let's not just go into that. There's no need for that. Okay, so just know relative humidity. So usually the readings from these two bulbs you minus to get your hygrometer reading or your humidity. Okay, you minus the one from the wet bulb from the dry bulb, of the one from you minus the one from the dry bulb from the wet bulb to get your final reading. Okay, as an estimate of your relative humidity, as an estimate. Let us understand surface tension. Let's just understand diffusion, osmosis, surface tension, all these types of force. All right. So diffusion is the movement of particles. Diffusion. When particles move, they move from region of what? Higher concentration towards lower concentration. All right, through a what? Or there is something that facilitates diffusion gradient. Until it happens, until a diffusion gradient is achieved. All right. For example, diffusion, you put, this is a jar. All right, you put iodine inside this jar. It's a solid. Okay, if you apply a little heat to this jar, the iodine is going to sublime and turn to gas. Okay, this is a higher concentration of iodine. Okay, this is a higher concentration of iodine. When you heat it up, it sublimes and it turns to gas. Iodine gas fill all parts of this what? This drum or this jar. That's called diffusion. A typical illustration of diffusion. You also have the one of bromine. Bromine can do the same thing, but you don't just need to heat bromine. Bromine is liquid at room temperature. So you get to a point, it starts diffusing. Liquid is a higher concentration than gas. It diffuses from liquid to gas. The particles move from liquid and turn to gas. That's what diffusion. Now let's look at osmosis. All right? Osmosis. So osmosis is the movement of water molecule, specifically water molecule, from a region of lower concentration to a region of higher concentration. Water molecule, the molecule of water, from a region of what? Lower concentration to a region of what? Higher concentration. All right? Don't forget this. All right? There is a semi-permeable membrane that it passes through. Through a what? Through a semi-permeable membrane. What's the meaning of semi-permeable membrane? It means that the membrane is selective. Not every molecule can pass through. Okay? Only water molecule can pass. Other molecule stays behind. So for example, let's say we have one bowl here, and here we put a semi-permeable membrane. Okay? They call this salt bridge. All right? This is the salt bridge. So here we have a solution of salt. We have a solution of salt here too. Okay? This solution of salt here is a concentrated solution of salt. Here is a dilute solution of salt. So this salt bridge is the semi-permeable membrane. Water molecule is the only molecule that is going to move. Salt molecule is not going to move. So it's going to move from a region of a lower concentration to a region of higher concentration. You know that this concentrated salt has lesser concentration of water because it is concentrated with salt. It is saturated with salt. So this side has more water because it is unsaturated with salt. All right? It is what? Dilute. So water molecule will flow, leaving the salt molecule here from this what? Salt, this salt bridge. This salt bridge is the semi-permeable membrane into this place. The exchange of this water molecule, or the movement, not specifically exchange, the movement continues until there is a balance in both sides, in the concentration on both sides. All right? So that's osmosis. The process whereby this water molecule moves is known as osmosis. All right? So let's quickly look at surface tension. Surface tension is the frictional force that exists in liquid on a surface. Okay? Where liquid thin out, liquid spreads into thin film. Let's say this is a table, for example. All right? This is the leg of the table. All right? This is the leg of the table. Okay? So, tea spill on this table. Okay? You are going to notice that the tea starts spreading in a thin film, or water spill on the table. You start noticing that it starts spreading in a thin film on the table. So that's, that force that enables that water to spread and stick to the table and spread in a thin film is known as what? Surface tension. All right? Surface tension. It's a frictional force. It's the force that makes liquid behave like stretched elastic film. Okay? Thin out. We already talked about capillarity. Now let's talk about force of attraction, the force of cohesion, and adhesion. All right? The force of cohesion is the what? Force of attraction between molecule of the same substance. Okay? Let's just put same substance here. Okay? Then adhesion. Adhesion is between molecule of different substance. Okay? Force of attraction between molecules of different substance. Different substances. All right? So, for example, what is cohesion? It's the force of attraction between molecules of the same substance, like force of attraction between gas molecule, for example. That is cohesion. Force of cohesion. All right? The force of adhesion is force of attraction between molecules of different substances. The substances is not of the same origin, but there's a force of attraction between molecules. For example, you carry gum, you gum your shoe. Okay? That bond that forms between that gum and the torn part of your shoe. The process is known as adhesion. The gum adhere to your shoe or the part that is torn. For example, I carry super glue and I rub it on my arm and I put my arm on the board. Okay, that force of attraction between my hand and this board. My hand is a molecule of a different substance. The board is a different substance. So that is known as what? The force of attraction, because it's a molecule of different substances. So what do we expect? What do we call it? We call it adhesion. All right, as simple as that. Adhesion. All right, force of adhesion. Let's look at heat transfer. Heat transfer. We have three major types of heat transfer. Okay, which is what? Through conduction, convection, and radiation. This is our final topic for this part, and we are going to look at the Thermos Flask thereafter. All right. So, looking at method of heat transfer, we start with conduction, where we have the successive collision of molecule. All right. Conduction. Number one, conduction. Method of heat transfer, conduction. All right. This is the method of heat transfer, whereby heat is transferred through successive collision of molecules. Okay. Just know that anytime you see conduction, just know that two surfaces are in contact. Contact is involved. Remember the conductors. Why they are called conductors of heat, okay, and electricity. There must be contact. Successive collision of molecule. Let's look at the second method of heat transfer, number two, which is convection. Okay, and convection is all about the heat transfer, the transfer of heat through upward and downward movement of molecules. All right, known as convection current. All right, to and fro movement of molecules. This is convection current. Okay, for example, you are attempting to transfer heat. Maybe someone's body is hot. All right, someone's body is hot, and you want to transfer the heat. You want to, bring down the temperature a little. Temperature is high. Person is running temperature. You can use conduction, which involves contact. So you bring an object that is a little bit cold. You put it, maybe ice block or a cold towel. Place it on the patient, okay, to help regulate the temperature. Or you can use what? Convection current, whereby you have to what? To pass water, pass warm water or cold water, tepid water, lukewarm water on the body of the patient, so that convection current can transfer heat, okay, from the point of higher energy, which is the patient that's having higher temperature, to whatever, substance that you are using to transfer the heat, or whatever substance you want to transfer the heat into. All right. So at number three, we have the final one, which is radiation. Okay. The radiation is the method of heat transfer, not necessarily requiring a material medium. All right. All this one, they require material medium. There is contact here. There is also partial contact here. Okay, but this one, no material medium is required. No contact. Okay. It is usually no medium. Okay. No material medium. All this place, you need physical material medium, but here you don't need any physical. That's why it's called material medium. Okay. You don't need any of those. Okay. But the heat is transferred through magnetism. All right. That's the method at which heat is transferred. So electromagnetism, or let's say electromagnetic wave. Let's use wave, because we are not talking about electricity. Through electromagnetic wave. Okay. Remember electromagnetic wave now. The spectrum. All right. So this is like infrared, for example. Infrared from a hot body. All right. So do not forget that radiation does not need contact, and it does not need a material medium. It requires no what? No material medium. There is something called temperature gradient. There is something called temperature gradient. Rate of change of temperature with distance. That is called temperature gradient until balance is stricken. All right. As easy as A, B, C, D. Let's look at the final subtopic before we call it a night. Thermos Flask. Okay. Conductors and insulators. What are conductors? Conductors are substances that are able to, that allow transmission of electrons. All right. They include metal, electropositive materials. Metals are good conductors. Most metals. All right. The non-conductors are materials or substances that does not allow the transmission of electrons through them. All right. So we have wood here, we have plastic. That's why they are used as insulator in wire, rubber, all of them. They are non-conductors. All right. So we are going to look at thermal flask, and we use this to call it a day in this episode. All right. So this is a thermal flask. All right. So we have something here. Again, this thermal flask, they took the set question from here. So let's bring this up. All right. So here we have something here called rubber cork. Rubber cork. All right. Then we have sieve or outer sieve coverage. Outer sieve coverage. Okay. Then which other thing do we have again in the thermal flask? We have the base. Okay, which is made up of insulator. All right, insulated base. All right, which other thing do we have? Okay, the vacuum between the wall, which is here, the vacuum. Vacuumized wall. Vacuumized wall. Okay, vacuumized wall. All right, let's see if we have any other thing again. Also, it has a double layer wall. Okay, that's why I put the double layer here, and that's that for that. All right. Okay, so severed surfaces. These severed surfaces, let's just put it as severed surfaces. It might be outer or inner. Okay, severed surface. So the thermal flask is used to prevent heat loss. All right, you can put an item here, a substance here, to preserve the heat content of the substance or the particular temperature of the substance for a long period of time. Remember that time when they put hot water inside flask? That's the typical example of it. It's thermal flask. So each of the accessories or the parts of the thermal flask, they all have their, their function, what they function as. They all have their duty. All right. For this insulated base, it prevents heat loss through what? Conduction. All right. Conduction. All right. Through surface in contact. All right. So heat can't be transferred because this is an insulator. It can't be transferred from a conductor to an insulator. All right. So we have this rubber cork preventing heat loss through, number one, you know that it fits tightly to this place. Okay. So it prevents heat loss through radiation and conduction. All right. It prevents heat loss through conduction because it tightly fits into the inner, the inner lining of the flask. All right. So that is how it prevents. That's the way it prevents heat loss from radiation. All right. So vaporized heat can't pass through and go out to the exterior. So let's just put it that rubber cork prevents heat loss by radiation. All right. Prevents heat loss through radiation. That's for the rubber cork. All right. Which other thing? If this rubber cork is removed, open, what happens? We are going to get upward and downward movement of molecule. Does that prevent upward and downward movement of molecule? It's just majorly radiation. Then these severed surfaces prevent heat loss through radiation too. Okay. Then for the vacuumized, the inner vacuumized, the inner vacuumized layer, okay, prevents heat loss through conduction, because it's preventing heat loss through contact. It's separated. So even though heat escaped, if the heat escapes, the heat will remain in this vacuumized area. All right. Then which other parts do we have here? Okay. Not just conduction, but through radiation. Okay. Because heat can radiate. Because if you keep a hot body here, heat can be radiated out of the body, especially if it's not double layered. But if it's double layered, heat is going to be trapped in this vacuum. And that helps maintain the temperature for a significant amount of time. All right. Thank you so much for taking this class. I will see you in the next part.